Welcome back. In this video, we continue our discussion on clustering, and specifically we will learn about the Gaussian mixture model. Gaussian mixture models, or GMMs, are a type of probabilistic unsupervised learning. Here, the goal in general is to specify a probabilistic model for our data, so write something like P of x given theta, where x is the observed data and theta are the parameters that we're trying to estimate. If we are going to build a useful model of our data, so maybe something that captures really the intrinsic structure of the data, we need to make some assumptions about how the data looks like or how the data is generated. Otherwise, there's no really hope. We can't really proceed without making any assumptions. Thinking back to our discussion on k-means, there we had the implicit assumption that every data point belongs to some cluster, right? We had these cluster indicators zi, which told us that the instance I belongs to cluster K. Well, here we're going to make that assumption explicit. Now, instead of modeling P of x given theta, we're going to model P of x and z, so we have a joint model of both the observed data point and its cluster indicator, and then we're going to optimize the parameters of this joint model. So how do we do this? Well, for modeling or for finding the optimal parameters theta here, or estimating the parameters theta, we're going to use the tools from supervised learning. So what we've already discussed in one of the first videos of in this lecture. Assuming now that for the moment we know the cluster indicator z and we know the observed data, if we have a joint model of x and z and some parameters theta, we can simply optimize the parameters to maximize the likelihood, right? We have a function. This is a function of theta, depends on x and z, which are both known for the moment. Simply maximize the likelihood and find the optimal parameters. But of course, the issue is that we don't really know the cluster indicators, right? We only observe the data x and we don't observe any clusters. Because if we did observe the clusters, right, then we're done. There's no need to do any modeling. So the question is, how can we find the parameters theta if we have only observed the data, right? So how can we estimate theta if z is unknown? And what we're going to do is the simple rule of marginalization. And just as a reminder, basically, you can represent the distribution of x given theta by marginalizing over x and z given theta. So we're going to sum up basically over all possible values of z, and this will be our p of x given theta, right? And now this is a function which again depends on theta. We only need the observed values of x because we're summing over all possible values of z, and we can maximize the function. We can maximize with respect to theta to obtain the best possible parameters, right? So usually when we have this joint distribution over x and z, we can use the product rule, and the way we write this down is that this is equal p of x given z. So if we know the cluster indicators, how would the data be generated? And then we also have additionally some prior over z. But in general, we're just trying to maximize the likelihood of the data given the parameters theta. So here just some vocabulary basically, because these cluster indicators z are never observed, they are essentially only an abstraction to help us simplify the model, and they're called latent variables. So in the previous maybe discussion on dimensionality reduction, we also had latent variable z, but now we just have a probabilistic treatment. We have some prior on this z, and then we have some distribution of how the observed data behaves given this z, and of course given the parameters theta. Okay, now this was in general how we would build a generative model given some latent variables, and now specifically we're going to discuss the Gaussian mixture model. The first assumption that we're going to make is the standard Iid assumption, which we almost always make. That is, we assume that the data is identically and independently distributed. So we have that our distribution over x and z given theta is a product over all I, p of xi, zi given theta. So we assume that all of the data points are independent from each other and that they follow the same distribution. And the way we specify this distribution, P of x and z given theta, the joint distribution over the instance and its cluster indicator, is via the product rule. So here we're going to decompose the joint into two parts, P of x given z and theta and P of z given theta. This part, P of z given theta, is what our assumption is about how the data is distributed prior to observing it. So how do we believe that the clusters are distributed before observing any actual data? And the other term, P of x given z and theta, is once we know the cluster indicator for certain instance, how do we believe that that instance is distributed? So this is so far pretty general, but now we need to specify these two parts, P of z given theta and P of x given z and theta, in order to obtain the Gaussian mixture model. For the cluster prior, we do the simplest thing possible, and we assume that it's a categorical distribution. So let's say that we have 3 clusters, which means that we have to specify this vector pi, which tells us what is the probability, what is the prior probability that we observe instances from each of these 3 clusters. Let's say maybe this is 0,2, 0,5, and 0,3. This means that we believe that the probability to observe instances from the first cluster is 20%, the probability to observe instances from the second cluster is 50%, and the probability to observe instances from the third cluster is 30%. And in general, if we have k clusters, then we have prior vector pi of k entries, and they are all non-negative and sum up to 1. So the cluster prior is just a categorical distribution. And then the term P of x given z in theta is now just a normal distribution. So once we know the cluster indicator for each of our data points, we assume that the data is generated according to a Gaussian distribution. So remember that the cluster indicators are one-hot vectors, right? So each zi is a k-dimensional one-hot vector, where if we have a 1 at position k, it means that this instance belongs to cluster k. So that's exactly what we specify here, that the probability of the instance x, given that it belongs to cluster k, given that we have a 1 at position zk, then we say that this is a Gaussian which is distributed with mu k and sigma k, with some mean and some covariance matrix. So in general, what we have is we have some mean and covariance for the first cluster, some mu1 and sigma1, mean and covariance for the second, mean and covariance for the third one, and then depending on which cluster our data belongs to, we use the specific mean and the specific covariance. So essentially, all of these data points in the blue cluster were generated from a Gaussian distribution with mean mu1 and sigma1. All of these over here had mu2 and sigma2, and all of these over here had mu3 and sigma3. Right, so pretty simple. The cluster prior is a categorical distribution, and the conditional distribution of the data given the cluster prior is just a normal distribution with some parameters mu k and sigma k. Now, this is basically all that we need to specify the GMM model. We have our distributions, we have our set of parameters. So in this case, it would be the pi vector, the prior vector, and also all of the mu k's and all of the sigma k's. And now we simply want to find the parameters which maximize the likelihood. Okay, let's see how, before going to actually seeing how the likelihood looks like, another way you can think about GMMs is in terms of their generative process. And the generative process looks as follows. We start with k components, or k clusters, and we specify some known parameters mu k and known means mu k and known covariance matrices sigma k. And also we have these prior cluster probabilities pi k for each cluster, right? So I didn't write this down previously, but basically we had this pi vector where this is pi 1, pi 2, and so on until pi k. So first what we do is we draw the latent cluster indicator. We really randomly sample in proportional to these pi i's, And based on that, we get to which cluster indicator does the data point belong to. And once we know that, we take the appropriate mu k and sigma k and then sample from the corresponding normal distribution. So if you want to generate a data set of n instances, you draw the cluster indicator, and then you go to the appropriate mean and draw from a Gaussian distribution. And repeat again, draw the cluster indicator, let's say it's 2, then you go to mu2 and sigma2, put them into a Gaussian distribution and sample from that. And you keep doing this until you generate n data points. Of course, in our case, we don't know mu, we don't know sigma, and we don't know pi. And we've only observed the result of this generative process. So we now assume that somebody has run this generative process, it generated all of the data points, and now we only see the data points, and the question is, how can we estimate the actual true parameters mu, sigma, and pi? To learn the parameters, we simply maximize the log likelihood of the data. Specifically, to specify the probability of a single instance x, given the parameters pi, mu, and sigma, we marginalize over z and use the product rule. So the probability of x is just a sum over all possible values that the latent cluster indicator z can take. And if we have k clusters, we have k such values. The prior probability, so how likely is to observe cluster z if we don't have any information, times if we know that the data belongs to cluster k, what is the probability to be generated, and this is just a Gaussian distribution with mean mu k and sigma k. So we see that the probability for instance x is just a simple weighted sum of Gaussian distributions where the weight is exactly proportional to the prior for observing that particular cluster. And this is where the name comes from. So it's a mixture model because it's a mixture of k different Gaussians, where the mixture probabilities depend on the cluster priors. So this is the probability for a single instance x. Now, if we want to compute the log likelihood for the entire data set, we simply sum the log probabilities for the all of our n instances. So we have n instances, and the log probability of the data is just the sum over those n instances log of this term, which is the Gaussian mixture term exactly. Okay, and how does this look like? What is the density of the Gaussian mixture model? Well, the way you can imagine it is you have this Gaussians, which are kind of specified by the mean and the covariance matrix. So this is the first Gaussian, mu1, so this is its mean. This is the second Gaussian, mu2, that is its mean, and the third Gaussian, mu3, with its mean. And they have different shapes, so these Gaussians are oriented in a different way depending on how the covariance matrix is specified. So if the covariance matrix is isotropic, which means it has some values on the diagonal and zeros everywhere, you're going to get a spherical Gaussian. But if you have some non-zero entries on the diagonal, you're going to get a Gaussian which is like an ellipse and slightly tilted. So yes, as I said, you have these individual Gaussians, and then you have on top of it these mixture probabilities, which are like 0,5, 0,3, 0,2. So the entire GMM density is basically the weighted sum of these three Gaussian components. And this is how this looks like. So if you sum up now the density at each of these points and multiply it with the prior probability, you're going to get a density which looks something like this. So this is shown in 2D. Of course, you can do the same in 3D or higher dimensions, where now again you have Gaussians with certain mu's and sigmas, and then you have some weighting probabilities pi k, and then you just sum all of them up, and you might get a shape that looks something like this. Okay, now when it comes to GMM, actually there are two different separate things that are happening, which we have to be quite careful about. So there's learning and there's inference. So in the learning part, we want to find the optimal values of the parameters. So this is what we talked about so far. We want to find the optimal pi, sigma, and mu star, which give us the maximum data likelihood. And this is basically specified by maximizing the log likelihood of the data given the observed instances xi. But of course, learning is not enough. What we actually wanted to do, if we remember back to the start of the video, is that we wanted to do clustering. And to do so, given some parameters p, mu, and sigma, we want to compute the posterior distribution of the cluster indicator z. So let's say now we've computed this optimal p, pi, mu, and sigma star. Now we want to also compute the posterior distribution of the cluster indicators. And this will give us what is the most likely cluster indicator for each of our data points. And this is also what we want to do. So we don't want to do just learning, we want to do learning and inference. And we'll see how to do both of these in the next slides. Let's start with inference, because to compute the posterior, it's a simple application of Bayes' rule. And even though this expression might look complicated, it actually is pretty simple. So let's look at how the Bayes' rule looks like in general, right? So the Bayes' rule says P of z given x equals P of x given z times Pz divided by P of x. And here we also have the additional parameters theta, so we add them everywhere after the condition. Just to make it clear, in our case, the parameters theta are pi, mu, and sigma. Right, so this is just a simple application of Bayes' rule where we actually already know how to compute each of these components. So P of z given theta, this is the cluster prior, and these are just the pi k values, where these are exactly how likely is to observe a certain cluster if we don't have any other data. The term P of x given z and theta, this is also what we know. We know that this is a Gaussian distribution with parameters mu k and sigma k. And we only need to compute the density of the Gaussian using these parameters at point xi, which we've observed. And the final term in the denominator, P of x given theta, we already also know how to compute this, and this is just marginalization over all possible values of z. So it's a weighted sum, it's a mixture of all k different components, of all k different Gaussians. Right, so we know how to compute P of z given x, which means we know that after we've observed the data, which is the most likely cluster assignment for each of our data points. So how would this look like in an example? Let's say we have 3 clusters, and they're specified with some parameters, some Gaussians with means mu and sigma k. Let's say this is the first cluster, or the first Gaussian, this is the second Gaussian, and this is the third Gaussian. And let's also say that we have some prior pi, where it's 0,33, 0,33, 0,33 repeated, meaning all of the clusters are equally likely before we observe any data. So the prior is just a uniform prior over the clusters. Now, for some data point, xi, let's say xi is over here, in order to compute the posterior, we just compute the density of this data point for each of the 3 Gaussians and normalize by the total sum. So we compute the density of xi under the green Gaussian, the density of xi under the red Gaussian, the density of xi under the blue Gaussian, and normalize by the total sum, where we also multiply with the prior. So in this case, the prior is always the same, so it will just cancel out, right? And this is exactly what we specified over here. So in this case, what this might look like, it might be that P of zi given xi and theta is something like 0, 1, 0, 1, 0, 8. So because in this case, xi is very close to this Gaussian, it will have much higher density under this Gaussian than these other Gaussians, and then when you normalize, it will get the highest probability. So in this case, the posterior probability that xi belongs to the green cluster is 80%, and for these other 2 clusters, it's 10%. So most likely, we're going to assign this data point to the green cluster. And here we already see one benefit compared to the k-means algorithm. So in k-means, we had a hard assignment that this data point belongs to this cluster, and that's it. Here we get a nice soft assignment. We get a distribution, posterior distribution of how likely is the data point to belong to each of the different clusters. Okay, we can see also how this looks like for all of the data points. So on the left, we see the ground truth. So we know that these are our known Gaussians, and this is how the actual cluster indicators look like. So this is not what we have observed, but here we're just showing it to see what happens. And this is the data we observe. So we only observe the overall data set, but we don't observe the colors. Now, if we know pi, mu, and sigma, we can compute them posterior in a simple manner using the Bayes rule. And this is exactly what is shown on the third plot over here. And we see that most of the time, this matches pretty well. But you can notice here in these areas where we have some overlap, because we're not completely sure whether we belong to the green cluster or the blue cluster, we get some sort of 50-50. So it's more likely to be to green or blue and less likely to be to red, but we're not quite sure whether it's blue or green, right? And this makes sense because we don't really have the ground truth labels. We only have the posterior distribution of the cluster assignments given what we've observed so far. One thing here I want to mention, which I've skipped before, is that this quantity, the probability that the data point belongs to cluster K, the posterior probability, is called the responsibility of component K for observation I. And yeah, so this will be useful later on, and we use this shorthand notation gamma of Zik. But this is just a name. What we're computing is just the posterior using the Bayes rule. Okay, now we move on to learning in GMMs, which is, as we said before, maximization of the log likelihood with respect to the parameters. Here, actually, it turns out to be more challenging, because if you look how this function looks like, if you have a look, you see that it's a sum of a log of a different sum. And log of a sum, it's a quite nasty term to deal with, and in general, we don't have a good way to handle these kinds of terms. So in general, in machine learning, when you see a log of a sum of something, usually you need some other tricks to make this work, and you can't compute the closed form solution. So what can we do here? Thinking back to the linear classification lecture, we actually had a problem which looked very similar. In that case, we had data where, in addition to the observed features X, we also had observed labels Y, right? So we had some data points, and we knew that these data points belong to class 1, these data points belong to class 2, and these data points belong to class 3. And in that case, estimating the parameters was pretty easy. We just fitted independently a Gaussian to each of these, right? So the optimal parameters was just the optimal Gaussian independently for each of the classes. So the trick why the problem was very easy in that case is because in addition to the observed data X, we also had information about the labels Y. Or translating that into the clustering case, if we had information about the clusters Z, then we can also pretty easily solve the maximization with respect to the parameters given both X and Z. But it seems that we don't know Z, right? That's the whole point of doing clustering, to find Z. Well, what we're going to do is we're going to do a simple trick. We're going to say, we're going to start with some randomly initialized pi 0, mu 0, and sigma 0. And given these randomly initialized parameters and the observed data X, we're going to compute the initial responsibilities, the initial posterior distribution. And now we're going to use this initial distribution to solve the easy problem. Okay, this seems like a random idea, right? We've started with some randomly initialized values, computed the posterior, and then using this posterior, we plug in Z and then solve the easy problem. As we'll see later on, that this choice is exactly the right choice, and this will end up giving us a lower bound on the problem that we're actually trying to solve. So instead of maximizing p of x given theta with respect to parameters theta, which we don't know how to do, we're going to instead maximize log of p x and z given theta, so the joint x and z given theta, where the z now comes from this distribution based on the initial beliefs. So again, we compute these initial beliefs, gamma 0, based on some initial guess how p0, mu0, and sigma 0 are going to look like, compute the posterior, and then use this posterior into the expectation here to get a term that is over jointly x and z. So here, just because this term actually looks very similar to what we had before, one more time to clarify, what we had before is log of p x given theta. And this is what we would want to optimize, but we don't know how, because this was marginalization. This was log of sum over all values of z, p of x and z given theta, right? And we don't know how to optimize this with respect to theta because we have a log over sum. So the sum is inside the log. But if you look at this term, this is slightly different. This is an expectation of a log, which is a sum over log, right? So if we write this down, then this is sum over all k, gamma t of z I k times log p of xi zi k given theta. Right, so here we have a sum of weighted logs, which we know how to handle, and up here we have a log of sums, and this is what we don't know how to handle. Okay, and then this already motivates what is called the expectation maximization algorithm, where we alternatively run two different steps. So we start by computing an initial beliefs, an initial posterior distribution for z, and then based on this initial posterior, so based on here gamma 0 of z, we can maximize the parameters pi, mu, and sigma of this expectation of log p of x given x and z given theta. And this is pretty easy. We know how to do this. We've discussed this in the linear classification lecture. Now, once we obtain new estimates for pi, mu, and sigma, so in the first iteration, now we can recompute the beliefs. We can compute now gamma 1 of z, so the next beliefs, and then iterate the process over and over until we converge. So let's see how that looks like one more time. In pseudocode, we start with pi 0, mu 1 to mu k 0, sigma 1 to sigma k 0. These are just some initial guesses of how the parameters might look like. Then we compute at every step the responsibilities. So this is how likely is that the data point belongs to each of the clusters based on the data that we've observed. And right, this is, we know how to do this. This is just the inference step, and this is just the base rule, right? We talked about this before. Now, given this guess for the responsibilities, we can compute, we can maximize pi, mu, and sigma by maximizing essentially this expression. And to estimate these parameters, we can do it in closed form. Essentially, it looks pretty simple the way you would imagine it. The mean is just a weighted mean of the data points, where the weight is proportional to the responsibility of that cluster. So if a data point is very close to the green cluster, it will contribute highly to the mean of the green cluster and not so much to the mean of the yellow and blue cluster. And something similar holds for the covariance matrix and for the posterior of how likely you are to be in each of the clusters, essentially. Sorry, for the prior of how likely you are to be in each of the clusters. And then we simply iterate between these two steps, finding the posterior of z given x and pi, mu, and sigma, and then recomputing the new optimal pi, mu, and sigma given our current beliefs. And at some point, we're going to converge. One more time, this is the inference step, or the expectation step, where we simply apply Bayes' rule. And the M step, or the maximization step, we maximize. So we maximize with respect to pi, mu, and sigma the expectation of log p x and z given pi, mu, and sigma, where the expectation is based on the beliefs that we calculated in the previous iteration. So z comes from gamma at the previous iteration t of z. And then we just iterate between these two steps. So how to get, let's say, the argmax here, how to get mu, sigma, and pi, you're going to exactly derive it in the in-class exercises or the homework, one of the two. Okay, so how does this look like? Well, if we have some data set, basically we'd start with some initial guesses. Let's say our initial guess is for the first Gaussian is this, and the second Gaussian is this. And then we compute responsibilities. Then we update the Gaussians, compute responsibilities, update the Gaussians, and so on. We continue until we converge to the final Gaussians. And this already should remind you a lot to what we did in k-means, right? In k-means, we started with some guess for the clusters, and then we updated which data point belongs to which cluster, and then we re-updated the centroids, and we continued until we converged. So here, basically, we do exactly the same thing, but we're just doing it in a probabilistic manner. Instead of having centroids, we have entire Gaussians, and instead of having a hard assignment, we have a distribution, we have a posterior distribution of which data point belongs to which cluster. On the following link, there's also a nice animation which shows you how this iterative update procedure plays out on some real data. Okay. Well, the next thing we want to talk about is that the EM algorithm, the expectation maximization algorithm, is actually much more general and applies to many different models beyond the Gaussian mixture model. Essentially, whenever you have a model of the form log p of x given theta, which equals log of sum over all z's, p of x and z given theta, whenever you have a model of such a form, you can always apply EM to get a solution, regardless of how this P of X and Z looks like. And actually, this it doesn't have to be a sum. This could also be an integral, and you can still apply EM. And in general, the way this looks like is two steps, where we first evaluate the posterior. Given the current guess for the parameters theta t, we evaluate the posterior of the latent variables z. Then, given this posterior, we maximize the parameters theta to get the new parameters theta t plus 1 by maximizing this expectation term, where the expectation is over the current beliefs. And usually, evaluating the posterior is pretty simple, and maximizing this joint likelihood. So this is important, right? What we're maximizing here is the expected joint likelihood. And this is much easier to handle than maximizing directly x given theta. So usually both of these steps become much simpler when we decompose them into an E and an M step rather than doing directly this log of p x given theta. And this seems to work, right? So we applied this in the GMM case. We seem to converge to some relatively good solutions. The question is, why is this justified, right? Why did it make sense that we evaluate the posterior and we maximize with respect to the current posterior? Seems like a choice that comes out of nowhere. The question is, can we theoretically justify this? And it turns out yes, because this value is a lower bound on this value. And we're exactly going to derive this and see why this holds. Let's start with any distribution p of x given theta, some latent variables z, and any distribution q of z. We're going to rewrite this term, log of p x given theta, into a more convenient form, which will reveal why what we did before makes sense. So the first thing that we do is we rewrite this as a weighted sum of terms that sum up to 1. So these QZ terms, it's a probability distribution, so these values are some non-negative values, and the entire sum sums up to 1. So basically here we haven't done anything, but we've just written it as a weighted sum, right? So this equals to maybe 0.1 log p plus 0.2 log p plus 0.7 log p, and so on. And of course, if we sum those up, we get log p, because all of these terms in front sum up to 1, because Q of z is a probability distribution. So here, be careful, this is not marginalization, it's just writing log p of x given theta as a weighted sum, where the weights are non-negative and sum up to 1. Okay, the next thing that we're going to do is we're going to use the product rule. So we use the fact that p of x and z given theta is p of z given x and theta times p of x given theta. Right? So from here we see directly that p of x given theta is p of x and z given theta divided by p of z given x and theta. And that's exactly what we've done here. We've taken this term and we've replaced it with this term. So this is just the product rule. Then we're going to just multiply by 1, which means we haven't changed anything, and the way we write the 1 is q of z divided by q of z. So again, so far nothing has changed. We always have an equality between these steps. Now we're going to do a slight regrouping where we take this sum and split it into two different sums. The first sum is this term. So we have sum of z qz log of px and z given theta divided by q of z. And the second term is the remaining part, so this thing, where we have sum of z qz divided by p of z given x of theta, given x and theta. But note that we can simply switch the sign. So if we say minus in front, then we can put p of z given x and theta on top and q and z on bottom. So right, so far nothing has changed. We've simply split. The red thing is the first term and the green thing is the second term. Where here additionally the sign has changed because we flipped the qz and pz from the numerator to the denominator and vice versa. Okay, but now we can notice that this term is basically just a expectation, right? So it's a sum of z qz of something, which means it's an expectation of something. And that something is exactly this term over here. Okay, so this is just an expectation of something, while the other term, this term, if you look at it carefully, you see that this is the Chao divergence between the Q of z distribution and P of z distribution. So if you remember when we talked about the Chao divergence in a couple of videos ago, the Chao divergence between two distributions qz and pz is minus qz log pz divided by log qz. And this is exactly what we have. So this is just the Chao divergence between q, whatever q we chose, and the posterior p of z given x and theta. And if you again remember the discussion on Chao divergence, we know that the Chao divergence is always non-negative. So it's always greater or equal to 0, which now means that this value, this expectation over here, is a lower bound on what we wanted to compute. It's a lower bound on p of x given theta. And because it's such an important quantity, we give it name with this loss L of q and theta. And it's a lower bound for any q of z, which is pretty important. And because the lower bound holds for any distribution q, the next logical question is, can we somehow choose the best possible q? Can we choose the q that gives us the tightest lower bound? And the answer is, of course, yes. And to see which Q to choose, think about the properties of the Chao divergence. So in our discussion in previous videos, we talked about that the Chao divergence is a non-negative number, and it's 0 if and only if the P distribution is equal to the Q distribution. So that's what we can do. We take Q, set it equal to P, P of Z given X and theta, and then this term, the Chao divergence term, will go to 0 and it will vanish. So now not only we have a lower bound, but we have a tight lower bound, meaning we have equality. So once again, if we set Q to be P of Z given X and theta, the Chao divergence term will go to 0, and then log P of X given theta will exactly equal to L, Q, and theta. And L, Q, and theta was this expectation here that we wrote or derived in the previous slide. So previously, we basically decomposed this into two terms, where the first term was an expectation and the second term was Chao divergence. And now, by carefully choosing Q, the Chao divergence disappeared, which means we only have this term on the left. And looking at the expectation carefully, we see this is almost what we were solving in the E step. So we see that we have this term, which can be decomposed into, again, this part plus this part, where this is just the entropy of the distribution Q, and this is independent of theta, so it doesn't change our maximization problem, while the second part here is exactly what we used to do the maximization in the M step. Let's look at an illustration to better understand what's going on. So what we wanted to do is maximize the data likelihood. We wanted to maximize P of X given theta. And as a function of theta, this is some complicated non-linear, non-convex function. And in this case, we're visualizing this as a 1D function. We basically assume that the parameters are one-dimensional, so we can visualize it and see what's going on. But of course, the same analogy holds in for many parameters in higher dimensions. So we wanted to maximize P of X given theta, or log P of X given theta, but we couldn't directly do this. And what we did instead is we constructed a lower bound, and then we maximized the lower bound. So basically, at each step, we construct some lower bound on this function, and then we maximize the lower bound. Then we construct a lower bound again, and we maximize the lower bound. And we continue doing this until we converge. And what was this lower bound? So this lower bound, as a function of theta, is exactly this expectation of Z coming from Q, some term, where this term was exactly this expectation over here. Right? So for any distribution Q, we got a valid lower bound, but then we chose a particular Q, and that Q was the posterior P of Z given X and theta, which we also called the responsibility. So if we plug in the responsibility into this L of Q and theta, we not only get a lower bound, but we get a tight lower bound. And visually what this means is that we get a lower bound which touches the original P of X given theta. So basically, this is a lower bound and this is a lower bound. All of these are potential lower bounds, but out of all of these, for many different Qs, we choose the one which is the tightest possible lower bound, and it's exactly here shown in blue. And this was also, right, the expectation where Z comes from the responsibilities of the same term. And this particular lower bound, actually any lower bound, is again a function of theta, which means we can just maximize it. And that's what we did in the M step. So in the E step, in the expectation step, we computed this expectation, which gave us a lower bound, right? Because that's exactly what we proved here. We showed that this term equals to this term for a particularly chosen Q. And then once we have the lower bound, we're simply going to maximize it. So starting at some particular theta t, we construct a lower bound which touches the original p of x given theta, and now we maximize the lower bound. We get a new theta t plus 1. Then we again construct a lower bound, find the maximum of this lower bound. This was the m step, get the new theta t plus 2. Then again at this point construct a new lower bound, maximize it, and so on. And if you do this, here visually it's already pretty clear that you're going to reach a local maximum of the original p of x given theta. So even though we don't have guarantees that we'll find the globally optimal solution, until at least we have a guarantee that we'll find a locally optimal solution. One more thing to note here is that in each iteration, in each EM step, our data likelihood either increases or it stays the same, which means we've converged to a local maximum. So again, when we're maximizing this lower bound, either at the new maximum we have a higher value of log px given theta, and this has to be at least the same or higher because this function is a lower bound of this function. Or if the value is the same as before, then we know that we've converged to a local maximum where constructing a lower bound again and again doesn't change anything. And this is exactly what is stated here, that as we're maximizing in the m step log of q theta with respect to theta, we either improve the likelihood or we don't, which means we've reached a local maximum. Okay, and in general, right, EM is a general method, applies to many different types of models when we have a latent variable structure. This includes GMM, of course, the Gaussian mixture models, and always we have these two steps, E step and M step, which iteratively improve the likelihood until we reach a local maximum. And in general, what we wanted to do is we wanted to optimize the log likelihood of the data, but we couldn't do this because this was a function log of sum of something, and this is pretty difficult to do. And then instead what we did is we constructed the joint probability, and then we maximized the expectation of the joint probability. So in the E step, we construct the expectation of the joint, and in the M step, we maximize the expectation of the joint. And we repeat this until we reach convergence. So far, in the entire discussion on clustering, we haven't addressed the elephant in the room, which is how do you choose the number of clusters k? Both in k-means and in Gaussian mixture models, we assumed that we know a priori the number of clusters, and then we ran either Lloyd's algorithm or the EM algorithm in order to find those clusters. But of course, knowing the number of clusters is a pretty big assumption, and in practice we never really know how many clusters we should expect in our data. Then now to choose the number of clusters, basically people have introduced different heuristics which we can use as a rule of thumb to know which value of k is a good value of k. One such heuristic is the so-called elbow or knee heuristic. So what we can do is we can try out different values of k, and then based on what is called the within cluster sum of squared distances, choose a value of k. So on the x-axis, we're gonna try different values of k, and on the y-axis, we're going to plot the within cluster sum of squared distances. So basically, you look at each cluster and you see how far away are these instances from the mean or from each other or something like that. And then when you plot this, usually you get a curve which looks something like this. And this curve, there's initially a very steep drop, and at some point it starts plateauing. And then at that point, exactly, usually it's a good choice of k. So here you have to be careful, because if you let k be as large as possible, so if k equals n, the number of instances, then of course you're gonna go to 0, because each data point is its own cluster. There's no variation within the cluster. There's no the within cluster sum of square distances is 0, which means you get a completely objective of 0. And of course, this is not what we want. We wanted to cluster our data points into some sensible clusters. And usually when this objective starts plateauing, it's a good value of k. We can also do something similar in the case of the Gaussian mixture model. So this sum of square distances is more suitable for k-means. For the Gaussian mixture model, we can instead plot the log likelihood, which is now an increasing function of k. So as we increase the number of clusters, the log likelihood gets larger and larger. And again, there's at some point when there's a plateau, and increasing k doesn't improve the log likelihood by much. And then this again is usually a good value of k. So as before, here be careful, because k equals n, every data point is in own cluster, every data point has as high likelihood as possible, and this is the degenerate case that we don't want to have. So in addition to this elbow or knee heuristic, which is called that way because these curves look like an elbow, either like that or like that, there's some other heuristics like the silhouette heuristic. And briefly what we do with the silhouette heuristic is that we take an instance and then we compute the average to the other instances within its own cluster, and then the average to the instances in the second closest cluster. And then we look at the difference of these two averages. So if we look at an example, let's say we have clusters such as that, and then let's say we pick this data point, which belongs to the red cluster. We have that the average to the distance within own cluster minus the average to the distance to the green cluster is a large number. And if this difference is a large number, this data set is well clustered. Or this data point, sorry, is well clustered. Now, if we have a different data point over here, then as we compute the averages to one cluster minus the averages to the other cluster, this will be a much smaller number, which means this data point is not clustered as well. And then what we do, so we compute this difference of averages for every data point, we average that, and then we get one number. And then basically, the higher this number is, the more we have captured better the clusters in our data. And again, we can plot it, find the bend in the curve, and choose this as our value of k. There's also the gap statistic, which looks at the within cluster variation and compares this to the within cluster variation of a uniform data in order to select k. But I'm not going to go into the details. Basically, there's many different heuristics that people have invented, and some of them work well, some of them work not so well. It all depends on what kind of data you have at hand. Of course, what you can always do is you can do cross-validation, where basically you take part of the data set, run clustering on it, and then use the holdout, the validation data, to evaluate how good is your clustering. So you can, in k-means, you can compute the distortion measure, the objective function. In GMM, you can compute the likelihood, and then you can choose k, the value of k, by maximizing the likelihood or minimizing the error on the validation data set, on the unseen data. So you can always just do cross-validation as we've done before in supervised learning. Now, when it comes to probabilistic models, we also have some other choices which are a little bit more theoretically motivated. And these criteria for choosing the number of clusters k are basically trading off how good the likelihood is versus how many parameters we need to estimate that likelihood. So, as I said before, right, if we increase the number of clusters k larger and larger, at some point every instance will be its own cluster and the likelihood will be as high as possible. So what we want to trade off is how many parameters are we using versus how high the likelihood is. And these two criteria, the Bayesian information criterion and the Aic information criterion, come from different motivations. So I think this one comes from information theory and this one comes from Bayesian analysis, but both of them basically trade off two terms, where the first term is the model complexity in some sense, and the second term is the likelihood of the data. So here I just want to apologize for the change in notation. Basically here k is the number of free parameters. And n is the total number of samples. So just be careful here, k is not the number of clusters, but just the total number of free parameters that we have to estimate. In Gaussian mixture models, let's say we have 3 clusters, then we have 3 times d for estimating the means, 3 times d squared for estimating the covariance matrices, plus 3 for estimating the prior probabilities, right? So the means are d-dimensional vectors, mu I. The sigma I are d by d square matrices, and then we also have the pi prior vector. So in the Gaussian mixture model, these were our free parameters. This is exactly what we were optimizing over, and you sum up the total number of free parameters, multiply by log number of samples, and this gives you the essentially the complexity of your model. And then you want to trade off the model complexity with the likelihood. And this actually holds in general. It is not only for unsupervised learning. Whenever we have a probabilistic model, we can count the number of free parameters and estimate the data likelihood and try to find a good trade-off between these two forces. So now what you can do is you can try different number of clusters, compute the number of free parameters, compute the log likelihood, which will then enable you to compute the Aic criterion, and then you see that you get a curve which looks something like this. So this is the number of clusters, and this is the Aic. You're going to get a curve which maybe looks something like this, and then simply you're going to choose the point, the number of clusters k, at which the Aic is as small as possible. The same thing holds for the Aic criterion. In this case, we see it's very similar, but we just don't have a term that depends on the number of samples. So in Aic, the number of samples is not penalizing, is not giving you higher model complexity. And this is because the Aic is derived based on some different assumptions about how the data looks like, and Aic again has some different assumptions. And whenever you use these heuristic methods, how well they work depends on how well the data that you're working with matches the underlying assumptions. And even though these are more thorough, they're more principled, they come from some theoretical background, they still rely on some assumptions, which means that they can't always work well in practice. Okay, now that you know how to choose the number of clusters, basically you have everything you need to know in order to do clustering in practice. Before we finish, I want to discuss a different type of clustering, which is called hierarchical clustering. And the idea here is to iteratively merge the instances until you get one big cluster. So this is the agglomerative version, where you start with all of your data points, merge them together into smaller clusters, then take those smaller clusters, merge them together, and continue doing this until you get one big cluster. There's also a slightly different variant, which is called a top-down approach, or a divisive variant, where you take one big cluster, you split it into 2 parts, then you split the splits, and so on until you reach certain single instances. So let me illustrate this on an example so it becomes a little bit more clear. Let's say we have some data, and let's say we have these instances. Maybe let's number them. This is A, B, C, D, and E. So if we look at the agglomerative approach, what we do is first we merge the instances which are most similar to each other. So A and B are quite close, they're quite similar, so that they get merged into their own small cluster. D and E are again similar, they get merged into their own cluster. And C, it's the only one left, there's nobody to merge with, so it's again its own small cluster. So now that you've done the first step here, we continue merging up until we reach one big cluster. In this case, it becomes slightly more tricky because now we have to think about what is the distance between these sets of data points? Is C more similar to the AB cluster, or is C more similar to the DE cluster? And as we see on the next slide, there are different ways to measure distances between sets of data points, but let's say we, for the moment, choose the smallest distance. So we take C, compute the smallest distance between A and B, versus computing the smallest distance between D and E, and choose the smaller of the two. And in this case, we can visually see that C is closer to A and B, so we're just going to merge this into one cluster. And in this case, D and E doesn't have any other cluster to get merged with, so it's on its own. And then we do the final step where we merge everything together into one big cluster. So the way this looks like, one way you can represent this is with a so-called Dendogram. Let me draw this. So we have our data points A, B, C, D, and E. And this Dendogram tells you what gets merged with what. So we know that A and B got merged, D and E got merged, and C was on its own. So this was in the first step. Then in the second step, A and B got merged with C. And then in the final step, this entire cluster ABC got merged with DE. And this representation here, it's called the Dendogram of the hierarchical clustering approach. And this works regardless whether you do bottom-up merging or top-down splitting. In both cases, you'll get a Dendogram. And this is what I show here on this image, where it's now done for a much larger data set. So we see that we have these small instances together, which get merged into a small cluster, then these get merged into a larger cluster, then these get merged into a much larger cluster, and so on until we get one big cluster overall. So the beauty about hierarchical clustering is that now you don't have to choose K. You can directly get any number of K by thinking about at which point of this Dendogram you're going to cut it, essentially. At which point of this Dendogram you're going to consider. So if I consider this point, this depth in the Dendogram, because the Dendogram is just a tree, then we see that we get two clusters, this one and this one. If I cut it at this depth, then we get three clusters. We get this one, this one, this one, and this one, actually four. And then depending on which level of the Dendogram you focus, you're going to get different clustering out of your data. So not only do you get clustering, but you also get some sort of hierarchical information. You know that these data points are similar to these compared to these are very dissimilar from these, and so on. And just like with k-means and similar distance-based approaches, how well this works depends on the quality of the distance function. So here I want to make one more point. It's pretty also important how do you choose which clusters or which subsets of data points get merged, and there are different criteria for this. One thing is the single linkage clustering, which computes the minimum sample distance. So you take one cluster, small cluster, another small cluster, compute the minimum distance of all pairs, repeat all this for all possible subsets, and then choose the smallest one. You can also use the maximum distance between all pairs in the subclusters. You can choose the average distance. You can compute the centroids and then the distance between the centroids and so on. So there are many different, again, heuristics which tell you how to merge or how to join together these subsets of data points. Okay, that was basically hierarchical clustering, where we recursively merge or split the data to obtain our clusters. But we're not going to go into more details because the lecture is already long enough the way it is. Okay, now let's just summarize what we talked about in this week on clustering. The whole idea of clustering was to group similar objects together. We want to find clusters such that the instances within the same cluster are similar to each other and two instances in different clusters are dissimilar from each other. We looked at k-means, where the algorithm took alternating steps where we first compute the centroids, then we assign each data point to the closest centroid, then we recompute the centroids by just computing the mean, and continue doing this until we converge. And we saw that K-means has some issues. For example, it can only find spherical clusters. It's not guaranteed to always work well, depending on initialization and so on. Then we introduced the Gaussian mixture models, which is very similar to K-means, but it's essentially the probabilistic variant of K-means. And the way we solved, the way we fit the Gaussian mixture model is with the expectation maximization approach, where in the expectation step, we compute the responsibilities, we compute the posterior distribution of the clusters given the data and the parameters, and then in the maximization step, we maximize the expected joint log likelihood. Here actually it's something interesting. You can even prove that if you have a Gaussian mixture model where the covariance matrices are constrained to be isotropic, and if you take the variance of the covariance matrices and you let it go to 0, then basically the GMM approach will converge exactly to the K-means approach. I think this is also part of the exercises, and you're going to exactly see how this happens. Okay, we also talked about how the expectation maximization algorithm is actually much more general, and that it applies in many different cases where you have a latent variable model. And basically, again, there's two steps, where in the expectation step, you evaluate the posterior with respect to the latent variables, and then in the maximization step, you maximize the expected joint likelihood. And finally, we talked about agglomerative clustering, where we recursively merge the data points until we get one big cluster, which gives us a hierarchical clustering. And depending on which level of the clustering we choose, we can get different clusters out of our data. Okay, so that was it about the clustering week. Next week, we cover some advanced topics in machine learning. I'm looking forward to talking to you about them. See you next week.